Our next speaker is Matías Guijarro. Matías has been working with Beamline Control Unit at ESRF since 14 years. He's responsible of the MSQ project for macromolecular crystallography experiments for many years. He's fond of Python and web technologies and is the team leader of the BLISS project that will be presented. The title of his talk is BLISS, Experiment Controls for ESRF EBS Beamlines.
So, thanks a lot, Guijarro. So, hello everyone. I'm very happy to be here today to talk about the BLISS project. So, BLISS is the new experiments control for ESRF EBS Beamlines. And I'm going to, as a preamble, I'm going to say a word about EBS. So, in fact, it's the EBS is the second phase of the ESRF upgrade. Basically, the accelerator is completely rebuilt to have a fourth generation light source. And there will be a very good talk about this with all the details on Friday by my colleague Jean-Michel Chaise. So I would just pass through this, and so the interested people can look at the talk from Jean-Michel. What I can say for us, EBS means new beamlines, new experiments, and new challenges. And here comes BLISS. So BLISS means Beamline Instrumentation Support Software, and it's a software package for experiments control and data acquisition. I think that I should give a bit of background on BLISS. So what we can say is why BLISS. For those who know ESRF, everybody knows that we are a spec shop. And so spec is driving ESRF experiments since 26 years. And in fact, spec is a commercial product from Certified Scientific Software in a US company. And so it's in ESRF since 26 years, and we have a lot of good things that we like in spec that are listed here, basically. So spec has direct control of the devices, which makes things easier to debug when we access our hardware directly. And if, for example, if we want to reset everything, we just have to restart spec. It more or less restarts, reinitializes everything from scratch. Spec is an integrated tool, so it has configuration, controllers for all kinds of devices, even a plotting facility. And since 2003, server mode has been introduced to connect with external processes like graphical interfaces, for example. And also we enjoy the commercial support from Jerry Swisslow, which is very responsive and professional. So all these are the good points in spec. Of course, as you expect, there are also some issues. So I would say, sorry. Oh, sorry. So there are also issues with spec. So the more important issue we have with spec is the poor macro language. So it's possible to have to write extensions, scripts and extensions macros, but the language is very poor, and there's no extensibility. Also, spec is a single task operation. So when spec is doing, for example, a scan, you can't do anything else with the same spec session. And spec has exclusive hardware control. So if you have hardware that is configured in two spec sessions, for example, you can't pass control from one or the other, so the two, in fact, it's stepping on the toes. And also, if we want to have multiple equipments in different sessions, we can't, because it's a per session configuration. No sharing between the configuration. Spec has no built-in scan framework for the continuous scans, so it also has limited data management, and of course we don't have the code ownership, so it's less freedom for us. So since 26 years, all those limitations have increased, and also we have tons of workarounds that also increase over the years, and finally the maintenance cost is quite high. So all those issues paved the way, in fact paved the path to BLISS. And so basically this is the talk outline. So we'll see all of these points. First, that BLISS is a Python library plus some tools. Then we will see the technical choices that drove BLISS design. And finally, then on the third point, I will talk about Beacon. And we will see hardware control, scanning and data acquisition, data management, and how we write sequences with BLISS. So BLISS is a Python library. So This is very important, and a set of tools. So I didn't lie. Here is why it's a Python library. You can see you can directly import BLISS from any Python program. So here we are importing BLISS to configure a motor controlled by an ISPAP motor controller, and then we can access velocity, acceleration, and all those parameters from the motor. Of course, this is not very convenient. And we built a command line interface called BLISS on top of PT Python. So this BLISS command line interface can load a session, as you can see, and it initializes hardware first, executes a setup file, and then we can, for example, start a scan. But we also have some other tools like a configuration web application to allow to change parameters or in the configuration directly from remote. And we also have a graphical interface for users, like an interactive web shell. So this is the scope of the project, from control to up to graphical interfaces. So we use, in fact, it's the same kind of shell as the command line interface, except that there's more graphical elements, like say synoptic, SVG synoptic or plotting. And now I will go to the technical choices to really detail what is BLISS from the inside. So BLISS, in fact, is built on 6 key concepts that are very important to us and that make, to our opinion, BLISS unique in a way. So the first thing is that BLISS is a single-threaded library, and we do cooperative multitasking thanks to Gvent. I detailed more, it's all detailed in the paper if you want more details. The second key concept of BLISS is directly inspired from spec, is the direct hardware control. And as a corollary, it comes with the third key concept, is that as we wanted to be able to control different hardware from different sessions, we implemented a distributed control ownership scheme with a shared state. I will detail that later in the next slides. We also have a persistent settings cache. And another very interesting and important concept for us is the generic scanning. So we represent all scans with an acquisition chain. And this acquisition chain is in fact a tree with master and slaves that works for all kinds of scans, continuous or step by step. And we will, of course, have a more detailed view on this later. And of course, and we also have from the scan data what we call the temporary data store. In fact, it's all data is published, so then an external processes can monitor that and for example, for online data analysis or data visualization. So how those key concepts are architecture, this is the, let's say, full picture, big picture of the project, which from your point of view, I think it looks a bit like all the same kind of projects architecture, except that devil is in the details, like always. So here we have what we call beacon services, which is basically configuration. It's in 2 parts. One is static, and one is more dynamic with settings, channels, and data publishing. And on top of the static part, objects are defined, and we have a communication layer for talking to hardware. And then on top of this, we have the hardware controller that makes, in fact, the hardware abstraction. And on top of that, we have the scanning layer, and finally, the data management layer. And all this is accessible from Python shell, every aspect of the project. So from the data management, we either publish data for online data analysis or visualization, or we store data for archiving. So now, a few words about Beacon, which is the central part of the project. Services for BLISS. So Beacon has a static configuration service. So we write the device configuration or sequences configuration in YAML format, which is an ASCII human-readable format. So basically, we define several objects in YAML files with name, and we can group objects in logical entities called sessions. And with sessions, we can associate a setup file and user scripts. And one interesting feature of the Beacon server is the ability to replace the Tango database server. So what we can have with this is a central place with all the beamline configuration, including Tango devices, in YAML format. And we have a web interface for configuration editing, as I said before. And how does it look like, this static configuration? Well, you see, you have a tree of files. These come from ESRF Beamlines, and those files contain those objects with names, as I said. And typically, I extracted a motor object from the files, so we define all the interesting parameters for the configuration. So in this case, the axis name is MBV4mot, and it's an ICALEPCS-driven motor. So the dynamic services provided by Beacon are all built on top of Redis. So we have the persistent settings cache. So basically, this is useful when, for example, we want to, among executions, we want to store the settings. It's a bit like Tango memorized attributes, for those who know Tango, or it's a bit like the settings in spec. In fact, for example, we keep velocity of a motor, you change velocity, you move your motor, and then you exit. And when you restart, you want to get back to the previous velocity. So this is all stored in the settings. And we have this transient data store for temporary storing acquisition data. And the message broker for what we call the state sharing and the distributed lock. And the next slides will maybe bring more light on this. So BLISS hardware control now. Basically, this is a big picture of all what I said up to now. So from the configuration here, we can see that the user is getting the PSZ1 motor. In fact, it's defined here. So from this, it instantiates the motor controller from the configuration. And then here we have a move command to move the motor. So it directly talks with the ICALEPCS controller. And while the motor is moving, the axis settings are updated and sent to Redis. So basically, this is how it works. And so if we think we have multiple BLISS processes, it means we need to handle concurrent access, manage concurrent access. So this is what we call the distributed control ownership. It's based on a protocol. So we ask Beacon for the permission, can I take this object? Is it free for me? And then the object is assigned to the coder. And if you have two different objects, and one instance is moving a motor, for example, on the other side, if you want to keep updated, for example, to know if the motor is moving or not moving. And so this is the state coherence, and this is shared between all peers via channels. So just to make a little example, here we want to move PSY1 from process A, so we acquire the lock, it works. Then we move the motor, and then while the motor is moving and the lock is acquired on the A process, the state channels are updated on the B process. Basically, this is very quickly to give you an idea of how it works. And okay, next part is the scanning framework. So the scans are all based on an acquisition chain, as I said before, which is a tree with master and slave nodes. And in short, masters, they trigger data acquisition, and slaves, they record, they save, take data. And in this acquisition chain, we put acquisition master and acquisition devices objects. And those objects are only wrappers around BLISS control objects, as we have just saw before, like the axis object. So there are as many different acquisition master and acquisition device objects as kinds of scans or types of control we want to do in a scan. And we have a last thing is the data writer, which is HDF5 based, because we all write data in HDF5 file format. Well, so the continuous scan example. So here there is a very simple example of a very classic dummy continuous scan. So we want to, when a motor is at constant speed, we want to trigger detector frame at regular intervals. So here is the code for this. And in fact, what we want to build is this tree here. So the motor is the master, and it triggers a Lima 2D detector device to take an image. So here there's the imports of the BLISS from BLISS. And here we define the acquisition chain. And here we have this software position trigger master. So here we give the motor object And this is one of those specialized acquisition master devices as objects, as I talked just before. And this is here the limb acquisition device. So we build the chain, and in fact, then we need to then we need to specify where to save the data, and finally to start the scan. That's it. So for step-by-step scans, of course, we have directly available functions like in spec, so A scan, D scan, all the scans in spec have been re-implemented. So we provide a default acquisition chain, and it uses the same underlying scan framework because in BLISS, all scans are the same, in fact. Data management, very, very quickly, because I'm getting out of time, but it's quite hard to summarize 2 years of development in 12 minutes. So, in fact, the model that we have for acquired data is a mirroring of the acquisition chain tree. As everything has a name and everything has a type and a shape, we can really make a model that is close to the experiment. We can also add metadata, and with this, we can publish to the Redis database all the scan data. So what we do is that the scalar values that are stored directly in the Redis database, and for all that is bigger than scalar values, a reference is stored with a configurable time to live, which means that after some time, the data is removed from this transient data store. And why it's like this is just to be able to perform online data analysis. For example, it can stay for a day or to do visualization. So user sequences, very quickly, you just write normal Python functions, and we use Python context managers for the cleanup, for example, or timeouts with events are very easy to do. So basically, it's very easy to write Python functions. As a conclusion, I would say that the current state of deployment of BLISS at ESRF, all MX Beamlines are equipped with BLISS already, and there will be 3 more Beamlines at the end of the year. And the goal, we aim for the full deployment in 2020 when we will have the new machine. And I can say that the project is in active development. Here is the GitLab board with all the issues and the tasks we have to do, the stories. It's not ready for use outside ESRF yet, honestly. And voila, we have a long-term project for ESRF for EBS Beamlines. What we try to do is to keep what works and try to add new concepts to circumvent limitations. And we have a nice scanning framework. Hopefully, we are prepared for current and future challenges, like scans with feedback or data management, and we have an evolutive platform. So I would like to thank all my colleagues from the development team, and also the BCU guys that contributed to the code, and the software group. And I thank you for your attention. I would be very happy to answer questions if we may have 1 minute or two. Thank you.
Yeah, we may have time for 2 quick questions.
Sounds very good. Thank you. Thank you for the presentation. I guess you have a plan to move because you have plenty of macros and spec deployments at the ESRF, and you're planning to move this in 2020. Do you have a plan for moving the macros, or you plan to move the macros one by one? Or?
No, I think the plan is to move the beamlines one by one. And in fact, little by little, if we carefully choose the beamlines, we can have a whole set of macros that will just go away, because in fact, we don't do the things now as we did 5 years ago or 10 years ago even. So we can completely, we have the scientists hand in hand work to upgrade also the experiments and the way we control the experiments. So I think it's going to be a beamline per beamline work, in fact, and we have a lot of work. Oh, and I forgot to mention that for the transition phase, because we still have, we can still use spec, all the BLISS devices, all the BLISS objects can be exported to Tango with an automatic device server that can generate objects. Yeah.
Let's thank Matthias again.